Okay, so today's lecture will be about doing calculus on parametric curves. What I mean by that is finding the slope of the tangent line and doing things like computing area and arc length. So let us get started. So 10.2 is calculus on parametric curves. And we're going to do most of the section today. We will have to continue it tomorrow. It's too long to do in one lecture. So let's consider a parametric curve, x equals x of t, comma y equals y of t. And we want to compute the slope of the tangent line. So maybe here's the curve. Here's the point on the curve, which is given at some time t by x of t, y of t. And we want to compute the slope of the tangent line. Okay, so how do we do that? Well, the slope of the tangent line is dy dx. And by the chain rule, for differentiation, that's dy dt, dy dt dx. The dt's cancel to give you dy dx. But we don't want to compute dt dx. We want dx dt, but that's the reciprocal of dt dx. So this is going to be dy over dt over dx over dt. Or if you like, dy over dx, the slope of the tangent line is y prime of t over x prime of t. And this is the slope at time t. So this is the slope of the tangent line at the point x of t, y of t. Okay, so that's part one of what I wanted to say about slope. I also want to talk about second derivative. Remember, the second derivative tells you about concavity. Well, what is the second derivative going to be? Well, it's d squared y over dx squared. And that's the derivative with respect to x of the first derivative, dy dx. Okay, but now what does that mean? What is that going to be? Well, that's going to be by substituting for y in the previous equation, we use the chain rule dy dx instead. That's going to be the same thing as derivative with respect to time of dy dx times dt dx by the chain rule again. All I'm doing is I'm replacing dy dx in the chain rule equation I developed in part one with dy dx itself. Okay, and again, we do the same game, right? dt dx is 1 over dx dt, so you get d by dt, dy over dx, divided by dx dt, and that's the answer. So that's going to be the second derivative. Okay, so it makes sense to try to do a computation. So let's do a computation in the simplest case I can think of. Let's do it for the circle. Okay, so I'm going to need to. Okay, so here's an example. Oops, let me make it in black. So let's find the equation of this tangent line to the unit circle at the point square root of 2 over 2, comma, square root of 2 over 2. That's a point on the unit circle. So here's what we're going to do. We're going to use the following parameterization. X equals cosine of t, y equals sine of t. And the point square root of 2 over 2 occurs at t equal pi over 4. So because the cosine of pi over 4 is radical 2 over 2, as is the sine of radical 2 over 2. Sine of pi over 4 is radical 2 over 2. So what is dy dx according to what we just did? Well, it's going to be y prime of t over x prime of t, which is cosine of t over the negative of sine of t. That's the, and what is that at t equals pi over 4? At t equals pi over 4, what do we get? We get cosine of pi over 4 over the negative of sine pi over 4, which is radical 2 over 2 over the negative of radical 2 over 2. And that gives me a slope of -1. So in order to get the equation of the tangent line, we have to use y equals mx plus b. And in this case, m is -1, so it's negative x plus b. And now we're on the unit circle at this point, radical 2 over 2, radical 2 over 2. We have to, so when x equals radical 2 over 2, so does y. So radical 2 over 2 equals negative x, negative of the radical 2 over 2 plus b to get these, the intercept b. So you're going to get b equals radical 2. And the answer is y equals negative x plus radical 2. That's the equation of the tangent line. That was pretty simple. So that's our first example. I'm going to save the slide, and now I'm going to compute the second derivative to the circle at that point. So example, find d squared y dx squared. In the previous example, at radical 2 over 2, radical 2 over 2. In other words, at i.e. at t equals pi over 4. Okay, we saw that the second derivative formula was d squared y dx squared is the derivative respect to time of dy over dx over the derivative respect to time of over dx dt. Now remember, x was cosine of t and y was sine of t. So what is, and we saw that dy dx was given by, remember that dy dx in the previous example was cosine of t over the negative sine of t. Okay. Now you could think of that as the negative of the cotangent, but we could also compute the derivative directly. We have to compute the derivative with respect to time of this. So what is d by dt of dy dx? That's going to be the bottom, which is negative sine t, times the derivative of the top, which is negative sine of t, minus the top, which is cosine of t, times the derivative of the bottom, which is the negative of the cosine of t. And I'm losing a little space here, but in any case, the bottom, and then over the square of the bottom, which is the negative of the sine of t squared. So this becomes sine squared t plus cosine t over the sine squared of t. So it's 1 over the sine squared of t, if I've done this right. Okay, so that's the numerator of the second derivative. It's 1 over the sine squared of t, also known as the cosecant squared of t. And what is dx dt? Dx dt is the negative of the sine of t. So the second derivative is negative 1 over sine cubed of t. So at t equals pi over 4, what do we get? We get the negative of 1 over radical 2 over 2 cubed, which becomes, it looks like to me, negative 2 to the 3/2 power, if I've done this right. Okay, so that's the second derivative. And it's concave down, and as you know, the circle is concave down at that point, at every point. Okay, so let's move on And the next thing I want to talk about is another example, which is the cycloid, computing the slope of the tangent line, actually the equation of the tangent line to the cycloid. Okay, so let's do it. The example of the cycloid, remember in the cycloid, x is r times theta. R is fixed, it's a constant, and it's r is theta, r times theta minus sine theta, that's x, and y is r times 1 minus cosine of theta. The cycloid was that curve we derived the other day. And theta is any real number, it's any angle, and we're interested at theta equals pi over 3. This problem is directly from the textbook. Okay, so at theta equals pi over 3, what is x? X is going to be r times pi over 3, which is 60 degrees, minus sine of 60 degrees, which is radical 3 over 2. And y is r times 1 minus a half, so that's a half. So you get r over 2. Let me just put that in, r over 2. Okay, so that's at theta equals pi over 3. So I'm interested in the slope of the equation of the tangent line at that point. So let's compute dy dx. Well, we have to calculate the dy d theta, and then compute it over dx d theta, and then evaluate at theta equals pi over 3. So what is y? What is the derivative of y with respect to theta? That's the derivative of r times 1 minus cosine of theta. So that's r times the derivative of 1 minus cosine theta, which is going to be the sine of theta. That's what you get, and then that's the numerator, and the denominator is derivative of x respect to theta, which is r times 1 minus cosine of theta. So you get sine theta over 1 minus cosine of theta, and we can evaluate this at pi over 3, theta equals pi over 3, and this will give the sine of pi over 3, which is radical 3 over 2, divided by 1 minus 1/2. And so you're going to get radical 3. So radical 3 is the slope of our tangent line. This is our slopes. So now what I want to do is compute the equation of the tangent line. So that's y equals mx plus b. And m here is radical 3, so radical 3x plus b. So how do we get the equation? We have to stick in a point. We need to know one point on our tangent line. Well, this point over here is a point on our tangent line. So we're gonna stick in x equals this expression. So what do we get? So we get y. Oops. So what do we get? We get r over 2 equals the slope, which is radical 3, times x, which is r times pi over 3, minus radical 3 over 2, okay, plus b, and then we can solve for b. And I solve for b. I'm going to let you do it. It just takes up a lot of room. It's a lot about elementary algebra, but you're going to get b equals r times 2 minus pi radical 3 over, no, that's not what you get. You get something a little different. You get 2 minus pi radical 3 over 3 times r. So therefore, y equals radical 3x plus b, which is r times twice minus pi radical 3 over 3. That's the final answer to obtaining the equation of the tangent line to the cycloid at that point. Okay, that's enough derivative calculation. Now I want to talk about the area problem for a parametric curve. So area. So we have a parametric curve. And let's recall that the area, if f of x is a function, and it's greater than or equal to 0, say, between t equals a and t equals b, we want to compute the area under the curve. So that's the area of this region here. And the area is given by the integral from a to b of f of x dx. And we can think of that as the integral from a to b of y times dx, because f of x is y. Y is thought of as a function of x. So now suppose the curve is not a function, it's given by a parametric equation. So suppose x equals x of t and y equals y of t. And suppose that t varies between two numbers, let's say alpha and beta. Okay, so t is varying. This is the time. These are the limits of time. And we want to calculate the area under the curve. Well, we could just copy the formula. The area is the integral of y times dx. But what is y? Y is y of t. And what is dx? Dx dt is x prime of t. So dx is x prime of t dt. So we just substitute that into this formula right here. To get the area is the integral from t going from alpha to beta. Don't be scared of Greek letters. Y of t times x prime of t dt. So that's the area formula. This is area. Okay, so let's use this to compute some areas. Let's do the area of a circle. So example area of a circle of radius a. So that would be the equation, the parametric equation, x equals a cosine of t, y equals a sine of t. And t should be going from 0 to 2 pi, because if it goes further, it goes around more than once. So the area is going to be the integral from 0 to 2 pi of, okay, so what is x of t is a cosine of t. I'm sorry. We first have to compute y, and that would be a sine of t. It's y dx, remember, or y of t, x prime of t dt. And that's the integral from 0 to 2 pi. What's y of t? That's a sine of t. And what is x prime of t? X prime of t is the derivative of a cosine t, which is negative a sine of t. And there's a dt. So this is going to be, if I did this right, it's going to be the negative a squared times the integral from 0 to 2 pi of sine squared t dt. And I'm worried about this minus sign here, and I'm probably getting the wrong sign. Well, let's not worry about the sign for now. Let's just do the computation. Okay, so what do you get? We know that we're going to have to take the absolute value anyway of this. So maybe that's where this is going wrong. So we'll take absolute value. Okay, so then what do we get? We're going to get a squared. Now we did the integral of sine squared of t. That's t over 2. This is from chapter 7 minus sine 2t over 4. And we're evaluating it from 0 to 2 pi. That gives me an a squared. So you're going to get 2 pi over 2, which is pi, minus the sine of 0 is 0. So you're going to get pi a squared, and that is the correct answer for the area of the circle. And we should have taken absolute value in defining the area. Remember, we had the assumption f of x was positive, right? Well, the curve in this case takes negative values. That's the problem. Okay, so we took the absolute value. We got the right answer. Okay, so the next thing I want to talk about is arc length. Okay, so let's recall what arc length is. Arc length of a function was L equals the integral from a to b of the square root of 1 plus dy dx squared dx. That's from way back when. Okay, so now what if you have x equals x of t and y equals y of t, and what do you get, right? So first of all, I want to, and let's say t is going from alpha to beta. I want to rewrite the expression 1 plus dy dx squared times dx. And the way I'm going to do it is like this. This is the same. If I bring the dx into the square root, I have to square it, and then I distribute, and this is the same as dx quantity squared plus dy quantity squared. Now I can divide by the expense of dividing by dt squared. I'll get dx dt squared plus dy dt squared, and the dt on the outside. So you can easily see that this last line is equivalent to the previous line. And this is the same thing as x prime of t squared plus y prime of t squared dt. So what this tells me is if I want to compute the arc length is given by the following formula of a parametric curve arc length. It's given by the integral from alpha to beta of the square root of x prime of t squared plus y prime of t squared dt. So that's the arc length formula. Okay, so that's we're going to use that now to compute the length of a circle, the circumference of a circle, and that'll be our last example for today. And then next time I'll continue talking about surface area for parametric curves when we do a surface of revolution. So here's the example. So let's talk about a circumference. Circumference of a circle. Let's just say circle of radius a. So I want to compute the arc length. So x is a cosine of t, y is a sine of t, and t is going from 0 to 2 pi. So we need to compute dx dt, which is negative sine of t. We've actually done that already today. And then we have dy dt, which is a cosine of t. And so then when we get the arc length integral, we get the integral from 0 to 2 pi, the square root of negative a sine t quantity squared plus a cosine of t quantity squared dt. And this simplifies greatly because of the trig identity. This becomes the square root of a squared, or a dt. And this integral just is 2 pi times a. And that is the well-known formula for the circumference of a circle. So there you have it. That's it so far with parametric curves. We're not finished with this section. This is section 10.2. We will continue next time and finish it off, and then do some more.